everyone. So it is 5:30 a.m. on Saturday morning before the ACT. I am pumped on tea and really pumped to do some enthalpy change right now. So we are going to go through slides. Let me tell you specifically. We're going to go through slides 30 through 43. So we're going to get through 13 slides today. I want to also tell you that not only will I be posting this video link for your blog, and the only real homework that you have this weekend is to watch the video and really understand what the notes are about. If you have questions, then post those on the blog or you can email me. But I am also going to post your pre-lab questions because we're going to do a lab on Tuesday in class. And that lab is going to be called Designing a Hand Warmer. So it will really go well with what we're going to talk about with this set of notes. But there are pre-lab questions, and that's going to be your homework for Monday night. But I wanted to go ahead and post them now, so then that way if you have extra time over the weekend, because I know we all have just so much extra time on the weekends, I know. But if you do have extra time on the weekend, then maybe you could go ahead and start answering some of those questions, or if you have questions about them, like, we can go through them and you can post those on the blog as well. So it's not just like a one-day thing. Okay, so let's go ahead and get started, but I kind of want to review a little bit first. So the last thing that we left off in class was talking about what enthalpy was, or what enthalpy is, I guess I should say. And we said that enthalpy is really just measuring heat flow, and we derived that whenever we were saying that my change in enthalpy is going to be equivalent to my change in internal energy plus this pressure volume work scenario. So the reason that we have to have the delta is because I can't just find enthalpy, or I just can't find the internal energy of a system just by itself. We can only calculate the change in those things. So that's why I have my delta sign there. Remember, we knew that our pressure, volume, work is just equivalent to work. So that's where I get, but it's work equals a negative P delta V. So if this is positive, then that work will be negative here. So that's where I get that negative work. I know from the first law of thermodynamics that the change in internal energy is equal to heat plus work. So I substituted that first law of thermodynamics into my delta E here to do that. And then if I look, the amounts of work will cancel out here. So I'm really just left with the change in enthalpy is equivalent to Q, which is heat. So if I could measure heat flow, I would know the change in enthalpy. So that's what this is trying to derive at. And we want to work on this in constant pressure situations, okay? So in terms of delta H, or in terms of change in enthalpy, so if change in enthalpy is only about heat and heat flow, would I be using the term exergonic and endergonic, or would I be using the terms endothermic and exothermic? I would be using the terms endothermic and exothermic, and that's because, remember, exergonic and endergonic are just about energy change in general, so that could mean heat and work. So it's not just heat specific when I use exergonic or endergonic. But when I talk about endothermic and exothermic, that is specifically terms used for heat flow. So a process is endothermic when my change in enthalpy is positive. So process is endothermic when change in enthalpy is positive. And that change in enthalpy being positive, that means that my system is going to gain some type of heat. So delta H is positive. So if we're going back to like our bank account analogy or our savings account analogy, I'm going to put some money in the bank, yo. Process is exothermic when delta H is negative. So if my change in enthalpy is negative, that means that my system is losing some type of heat or losing that energy. So in that case, Mama needs to go shopping for herself and baby Ella, so she's got to take some money out of the bank. So endothermicity, exothermicity, we can use those terms with change in enthalpy, because change in enthalpy is really just trying to calculate that heat flow. Okay, so I want us to try to practice kind of figuring out what the sign would be then for delta H here. Now, in the first case, it says, indicate the sign of the enthalpy change, delta H, in the processes carried out under atmospheric pressure, and indicate whether each process would be endothermic or whether those processes would be exothermic. So in the first one, it says that an ice cube is going to melt. So I want you right now to try to think, would this have an enthalpy change that's positive, or would delta H here be negative? I'm going to give you a minute to think. So in this case, if I have an ice cube's melting, that means that I must have energy going into that ice cube to raise the temperature for it to move from solid to liquid. So if I have energy that's being applied to that ice cube, there's energy moving into the system, that ice cube's absorbing heat from the surroundings, so that means delta H must be positive. So if delta H is positive, would that be an endothermic reaction or an exothermic reaction? If delta H is positive, it's absorbing, the system is gaining energy. I'm putting money in the bank, so that means that it has to be endothermic. Okay, let's look at B. On B it says 1 gram of butane is combusted. Key word here is combusted. So 1 gram of butane is combusted in sufficient oxygen to give complete combustion of carbon dioxide and water. We know that in combustion, we have to have some type of energy that's released because we're creating carbon dioxide gas, we're creating water vapor. We know that we have some type of energy that's releasing in combustion. So if I'm releasing energy, that means that the system is losing energy in the form of heat. Then that means that the surroundings are gaining it. So my delta H, my change in enthalpy, if system is losing, must be negative. So would this be an endothermic reaction or an exothermic reaction? This would be an exothermic reaction. Okay, I have one more down here, and I'm hoping that you can see the whole thing. This says molten gold poured into a mold solidifies at atmospheric pressure. With the gold defined as the system, is the solidification an exothermic or an endothermic process? And I'd like you to explain why. So I have some gold, I've poured it into some mold, and then it solidifies. And I want to determine, is this going to be exothermic or endothermic? And I want you to tell me why. So what do we think here? Exothermic or endothermic? This process would be considered exothermic. So why would this be exothermic? Well, I'm starting off with molten gold and I'm pouring it into a mold. So that means I have liquid gold right now. And that liquid is going to turn into a solid because it's solidifying. So if my liquid's turning into a solid, then I'm going to have to be... Oh my gosh, guys, my Promethean board shut off. Give me just a second. Okay, it's going to come back on. I'm so sorry. I don't know why it shut off. Okay, so we had our molten gold, and it was solidifying. We said this is an exothermic process because I am going to have to release some type of energy for those molecules to start to solidify for the gold. So the system, being gold, is going to release energy to the surroundings, so then that way it can come together to solidify. So if it's releasing energy, then it must be, a delta H will be negative, which means that I have an exothermic process because I am releasing that energy. Okay, so let's keep going. Now, an enthalpy of reaction. So let's move to that. The enthalpy change that accompanies a reaction. We just call that the enthalpy of reaction. So it's really simple. if I have a reaction and I want to know what the enthalpy change of it is, we're going to calculate something called the enthalpy of reaction. It's really that simple. So we sometimes call this, though, heat of reaction, because for us, remember, we said that really the change in enthalpy is also just finding heat flow. So I can call this enthalpy of reaction, or I could call this heat of reaction. Now, the change in enthalpy, delta H, is the enthalpy of the products minus the enthalpy of the reactants. So again, remember we did this with internal energy, for the change in internal energy, where it was my final internal energy minus my initial. Well, this is really the same thing, because the products is what I'm ending up with, and the reactants is what I've started with. So my change in enthalpy is just the enthalpy of the products minus the enthalpy of the reactants. Now, this is another energy diagram, and it's just showing that I'm going to react methane gas, with oxygen gas. So I'm going to combust methane in air, and I'm going to produce carbon dioxide and water. If, for example, I have two different values here, so with those,